My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 229. In this lecture, we will try to understand an alternative interpretation of principal component analysis. This alternative interpretation name is distance minimization interpretation. We already discussed in lecture number 228 one interpretation of PCA. That interpretation is known as variance, what it says, variance maximization interpretation. What is that interpretation name? Variance maximization interpretation. Here, what we did in variance maximization interpretation, find U1 which maximizes projected variances. This is about our previous lecture that is known as variance maximization interpretation of principal component analysis. Now we will try to understand another interpretation. That interpretation name is distance minimization interpretation. Imagine if I have my features F1, let me say this feature 1, let me say this is my feature 2. Imagine if I have my points like this, just assume these are my data points. Let me say about my previous lecture, that is lecture number 228. What we did, we want to find U1 which maximizes variance or spread. This we discussed in my previous lecture, that is in lecture number 228. This was the first formulation. Variance maximization is first mathematical interpretation. Now I am going to discuss second mathematical interpretation, that is known as distance minimization. There is an alternative interpretation to principal component analysis, which I take the distance of each of these points. What does it mean? Let me repeat. I take the distance of each of these points to this line. Let me say this is my U1. Let me write this direction. This is U1. Let's calculate. Let me say this is my D. Let me say this is my D1. Let me assume this is my D1. Let me assume this is my D2. Isn't it? Let's call this one is D1. Let's call this one is D2. So on, so forth. For each point xi, I can say like this. For each point xi, I can get di distance. For x1, I will get distance d1. For x2, for x1, I will get distance d1. For x2, I will get distance d2. So on, if there are n points, I will get distance dn, isn't it? I can get di for which the distance from xi to ui, isn't it? d1 is x1 to, this is distance of x1 to u1. This is distance, d2 is distance from x2 to u1, xn to u1. I can find all these distances, isn't it? Now, in the distance minimization approach, what I have to do? I must, as I told you, I must minimize the distance. We can write the optimization problem as follows, that we want to find, I can say like this, we want to find we want to find u1, such that sum of the distance squares, this sum of the distance squares, what I have to do? I must minimize this. I must minimize sum of the distance squares. What is di? What is distance d1? Let me say like this. Let me write in fresh present PPT. Let me say like this. I want to express, let me say, my xi. What is my xi? Let me assume my xi is somewhere here. Let me say this is xi. This is my u1, isn't it? Let me say this is my u1, isn't it? Now, what is my di? Di is distance between xi. Let me say this is xi. This distance. This distance, let me assume di. This is u1, isn't it? Now, what is this? Let me say this is my xi. I can say this particular one. Let me say like this. I need this distance, isn't it? I need this distance. Now, I have xi. Xi is my data point. I have my u1. This one, u1. What is di? I want to find this distance. What is di? In terms of, what is di? In terms of u1 and xi, isn't it? This is called distance minimization. I must minimize this distance minimization formulation of principal component analysis, because what we are doing, we are trying to find u1. Here what we are doing, we are trying to find u1 such that if I take all the distances from each of my points, all these distance squares, so this distance squares, I must calculate sum of all this distance squares and I must minimize. If I sum up all of them, all of the distances, I want to minimize the distances. So let's understand these distances slightly in more details. So let's assume let's assume these are two axes. This is F1 axis. This one is F2 axis. Let us assume I have one point here. This is my point xi. Let's just call this point is xi. One of the points. Let us assume this is my direction. This is my u1. U1. Again, in this case, I am going to assume u1 is unit vector. My assumption is u1 is a unit vector. u1 is a unit vector in the direction. u1 is a unit vector in the direction of f1 dash. This is f1, this is f2. Let me say this is f1 dash, isn't it? In the direction of f1 dash that we are interested in. What is the unit vector? We already discussed what is unit vector. u1 transpose u1 equal to 1, whose norm is 1. Now, what we want to find is the distance. What we want to find is the distance di. Now I need what I need. I need distance di, isn't it? What is this distance? This is perpendicular distance. This distance is perpendicular distance. Let's try to use Pythagoras theorem. Just try to recall Pythagoras theorem. According to Pythagoras theorem, you can find this distance. But before finding this distance, how can I say what is this? What is this part? What is this part? This part is essentially, how can I write? Projection of xi. This is projection of xi. Projection of xi on u1. Isn't it? This distance is projection of xi on u1. Isn't it? Now, what is the length? The length. What is this length of the vector? This length. What is this length? This length is essentially, I can say, norm xi. Norm means length. Now, I know this distance, norm xi. This is nothing but projection of xi on u1. Isn't it? Now, what I must minimize. I must find u1 such that minimize sigma I equal to 1 to n di square. Isn't it? That's what this distance minimization formulation of our PCS is. How will it be? How can I find? It is simple. Now, let me find this distance as it is projection of xi on u1. I can write in my previous lecture, that is in lecture number 228. I already discussed this one. As u1 is unit vector, projection of xi on u1 is essentially u1 transpose xi. This I already discussed in my previous lecture. By now what we know? We know this length, that is u1 transpose xi. We know this length, that is norm xi. According to Pythagoras theorem, what can I write? Isn't it? Norm xi, this hypotenuse whole square equal to what can I write? I can write it as di square. This is according to Pythagoras theorem, plus u1 transpose xi whole square. Isn't it? Now, let me write it in fresh slide. Just let me write like this. Therefore, I can write di square is equal to norm of xi whole square minus u1 transpose xi whole square. Can I write like that? Yes. By definition of norm, I already discussed in our previous lectures, this can be written as xi transpose xi. This can be written as like this. Isn't it? In projection lectures, dot product lectures, I explained this concept. I can write it as u1 transpose xi whole square. This is di square, isn't it? We want to minimize, we want to minimize the sum of the distance squares. Sum of the distance squares, isn't it? Therefore, what will I write? Can I write like this? Minimization of, you have to find u1 such that you must minimize sigma I equal to 1 to n xi transpose xi minus u1 transpose xi square. Isn't it? This is, isn't it? You have to find u1 such that the sum of all these things must be minimized. Let me say this is first one. What is your constraint here? What is this? Xi transpose. This is essentially this whole part. This whole part is, I can say, this whole part is, what is this part? This is di square. I am minimizing distance di and I am finding u1 such that this distance is minimum, isn't it? What is your constraint? What is your constraint? Again, u1 is unit vector, isn't it? Of course, what is this xi? Xi's are known because xi's are nothing but they are part of your data matrix. What is your data matrix? Data matrix x equal to, I can write like this, xi transpose, isn't it? This is my data matrix which I discussed. You are given xi's. This, we know what is xi, and you have to find u1. What you have to find? You have to find u1, which minimizes this distance. As I told you, xi's are part of your data matrix. Again, there is one more constraint. What is this constraint? As we assumed that u1 is unit vector, therefore u1 transpose u1 equal to 1. Isn't it? Let me say, this is first formulation, isn't it? This is minimization formulation. This is constraint. This is again, what is this? This is objective function. This is objective function, isn't it? Objective function. What about this? This one is constraint. Same constraint which we have seen in previous lecture, isn't it? Now, let me say this is first formulation, isn't it? Let me assume like this. You might say this problem is similar to previous problem, isn't it? Let's go and look at the previous problem. What is my previous problem? Just recall my previous problem in previous lecture. What I discussed. Just let me write like this. How can I write? Just see. This is my previous problem. Maximum, let me say this is u1, 1 by n, sigma I equal to 1 to n, u1 transpose xi whole square such that, what is the condition? What is the constraint? Such that u1 transpose u1 equal to 1, isn't it? This I discussed in my previous lecture. The constraints that we just saw are same. Means in minimization interpretation and maximization interpretation, you have same constraints. We have to minimize. In the case of minimization, even in the case of maximization, we have same constraints, isn't it? That means I can say in this way that got variance maximization problem. This problem I can say, I can just recall this one is, this formulation is variance maximization approach, isn't it? Variance maximization approach. What about this one? Let me say this is second one, isn't it? First one is distance minimization and second one is variance maximization. Constraints are same in both problems, but objective function is different. Here objective function is, this one is objective function. Compare these objective functions. These objective functions are different. But which one are same? Constraints same. Constraints are same. There is some similarity. Just see this, let me say u1 transpose xi whole square. Here also you have u1 transpose xi whole square. There is some similarity. If you speak strictly, these two formulations are equal. These two formulations are equal. How one can prove? There is, you can always, we can show with some transformation, we can show both objective functions are similar. Anyway, constraints are same. Even we can show that both objective functions are same. Both objective functions means objective function in distance minimization and objective function in variance maximization, they are same. So we will show that one of the things that we will show that u1 that minimizes u1 that minimizes with this constraint and u1 that maximizes with this constraint. They are same, they are similar, they are not different. I can say alternative formulation of PCA, and this is, I can say, distance minimization approach. I can say it is an alternative formulation. These two formulations are simply same. I want to introduce in optimization chapter. In optimization chapter, while we learning optimization, I will prove these two are equivalent. Let's just assume that we know how to solve this from now the exact process. Just understand the formulation here. I will explain how these two formulations are equivalent in my optimization chapter. I will discuss about optimization, where we will learn about differentiation, partial differentiation, maximization, in minimization. There again I will come back again. I will revisit this PCA. I will fill the gaps. Time being, just believe me, these two formulations are exactly same. Just you can see that constraints, anyway, both constraints are same. In terms of objective functions are also they are similar. We will prove in my optimization classes. Just go through this lecture. If you have any difficulty, just keep a comment. Thank you very much.